This lesson is an intro to polar coordinates, what they are, and how to find the distance between them. So, rectangular coordinates are when we have this xy plane, and we have a point like 5 radical 3 comma 5. So 5 squared root of 3, so somewhere around 8, between 8 and 9, comma 5. So we have a point right there. The two numbers, the x and the y coordinate, represent from the origin how much to the right we go, 5 radical 3, and then from there how much up we go to get to that point. But there is another way to get to that point. Like if I was telling somebody to go here from this origin, I could tell them, walk east 5 radical 3 and then go north 5. But it would be faster to tell them to just go directly there. But to tell them to go directly there, I'd have to tell them what angle to kind of be pointing in. So if I draw this triangle here, and I call this theta and this r, theta is tan inverse, this is 5, of 5 over 5 radical 3, which ends up becoming 30 degrees. And r is 10. You could get that by Pythagorean theorem, or because in a 30, 60, 90 triangle, the hypotenuse is double the length of the shortest side. So another way I could describe how someone can get there is with two numbers, with two numbers, which I'll describe as, I'll put them in these braces instead of with the curvy braces, where the first number is sort of how far are you going to walk, and the second number is what angle. Now you might think, oh, I should say the angle first, because if I was actually telling someone what to do, I would say, hey, first rotate yourself 30 degrees, don't point east, but go 30 degrees in this direction, and then walk forward 10. But that's just not how these, what are called polar coordinates, are just defined. They're defined as r comma theta, where the theta here is the angle you rotate, and the r is the distance forward. Now there is something called polar graph paper, which looks like this. So in polar graph paper, we don't have horizontal and vertical lines, but we have these concentric circles and these almost like spokes of a tire. So if I want to graph the polar coordinate 10, 30 degrees, and I have this kind of graph paper, it's really easy because all I have to do is go on this 30 degree line and go out 10. I think this is 10, 1, 2, 3, 4, 5, 6, 7, 8. I think it's that point right there. So if it's already in polar form and you have this type of graph paper, the angle tells you which line you're going to be on, and the number tells you how far out you're going to be. And here I have the polar and the rectangular on the same page, and we can see here these are so 1030 would be right here. So that point could be described as 10, 30 degrees in polar. Or if I think about it in rectangular, it would be 5 root 3, 5. And you can see that it is actually there. There's 5. And down here, somewhere around 8 is 5 root 3. So those are two different ways to represent the same number, whether we're imagining a rectangular grid system or a polar grid system. Coming back over here. So here's a point, 5, 75 degrees. So that's going to be on the 5th circle, but at the 75 degree mark, so that's going to be 1, 2, 3, 4. It's going to be over there. Okay, so that's 5, 75 degrees. You might wonder, well, what is that? How do I convert from polar to rectangular. Well, converting from polar to rectangular is pretty easy because we imagine this triangle, and the y value is going to be 5 sine 75, and the x value is going to be 5 cosine 75, which is going to be about 1.3, comma 4.8. So to go from polar to rectangular, r theta to xy, we can say that x is equal to r cosine theta and y is equal to r sine theta. That's going to be the conversion. To go in the other direction, where I have it in rectangular and I want to change it back to polar, is going to be a little bit harder. So imagine I have the point 10, comma 2 in rectangular, which is somewhere over there, and I want to change it into polar. Well, that's the x and the y, and here's the r and the theta. So r is going to be the square root of 10 squared plus 2 squared, which is approximately 10.2. And the theta is going to be the tan inverse of, in this case, 10 over 2, but I'm going to put little absolute values around those. I'm not going to write theta, I'll write alpha. We have a reference angle, which is, it's 2 over 10. So the reference angle is about 11.3 degrees. And that's also theta in this case. We do have to keep track of what quadrant we're in. But for this one, we're in quadrant 1, so it's 11.3, it's 10.2, comma 11.3 degrees. 10.2 is the r, this is the theta. If I want to make like a rule out of that, I suppose the rule would be that this is from rectangular to polar. The rule would be r is equal to square root of x squared plus y squared, but that theta, depending on what quadrant I'm in, is either tan inverse of y over x, that's for quadrant 1, or it's going to be 180 minus tan inverse, I'm just going to say absolute value of y over x, so we just don't put negatives in there. If it's in quadrant 3, it's going to be 180 plus tan inverse of y over x, or 360 in quadrant 4 minus tan inverse. And if you remember from previous lessons when we did complex numbers to trigonometric form, this is going to be like the same idea. You should look at those videos for doing conversions. Now, if I graph 5, comma 30 degrees, well, that's going to be a point 1, 2, 3, 4, around there. If I graph something bigger than 360 degrees, like 5, 390, well, 390 is in the same place as 30 degrees, so 5, 390 is at the same location as 530. So that's different from rectangular, where if you have two different numbers, you're definitely going to get a different point. Where in this, we could get 2 points that are in the same location. And the r value actually can be negative. So like negative 5, 210 degrees. Okay, so the way that works is you tell the person, face in the direction of 210. So they're facing in that direction. And then you say walk backwards 5 units. Well, that person ends up at exactly the same place. This is something that didn't happen with trigonometric form of complex numbers, where we had negatives. I could also say negative 5, negative 150. Because negative 150 is actually in the same place as 210 degrees. So So they add up to 360. So this also gets me to the same location. So these are four ways of describing the same location. So that's one of the things that makes polar a little bit confusing. Now, if I take something like 0, 0, I end up right here in the center. It's called the pole. But if I do 0, 30 degrees, so I turn 30 degrees, but I walk 0 units, I end up there also. So this is extra confusing because no matter what the other number is, the angle, if the R value is 0, it's going to be located there at the pole. Okay, now I want to show you how you could find the, there's one quick thing I'll do first just to, so 3 plus, sorry, the 3, 4, that rectangular coordinate of 3, 4, why don't I do it on this guy? So over 3, or I'll say 4, 3, 4 is good. So somewhere over here. To change that into polar, we would do R is equal to the square root of 3 squared plus 4 squared. Why don't I make this minus 3, 4? Still ends up being 5. So I still have 5, but for the angle, minus 3, 4 is up here in quadrant 2. So theta is going to be 180 minus tan inverse of 4 over 3. See, I don't worry about this minus here. And when I pop that into the calculator, it ends up being about 137 degrees. I think it's 53 degrees is what this is. And then 180 minus this is 137. So I just want to, even though it's in another video, I thought I should mention that. Okay, the last thing in this video is how to find the distance between 2 points when they're given in polar. So here I have 2, 30 degrees and 5, 150 degrees. And graphing them is easy enough. There's the 230, and here's the 5. Here I can see 150 listed out there. 1, 2, 3, 4. And they want to know the distance between those 2 points. Well, one way to do this would be to convert them both to rectangular and use the formula for rectangular distance. But there is a shortcut. And the shortcut works like this. We make a triangle with the pole as one of the vertices. Now, 2 of the sides of this triangle are known. This is 5, because this point had an R value of 5. And this is 2. So I have this triangle with the 5 and the 2. And I'm going to use the law of cosines. The law of cosines is when you know 2 sides and the angle between them. But I don't quite know this angle like right away, but if I think about it, the 150 is from here all the way to there. And the 30 is just from here to here. So if I subtract those two things, 150 minus 30, is 120. So this triangle, which I'm just going to draw like that, that's a perfect question for the law of cosines. C squared equals A squared plus B squared minus 2AB cosine C. So this ends up, well, cosine of 120 is negative cosine 60, which is negative 1/2. And that's why this thing becomes 25 plus 4 plus 10, which is 39. So the distance is the square root of 39. So that's how you could, if you're someone who really likes formula, we could write it as a formula. G squared equals R1 squared plus R2 squared minus 2 R1 R2 cosine theta 2 minus theta 1. The order doesn't really matter because cosine of a negative is the same thing as cosine of just the regular. And that does it for this lesson.